new technologies in protecting oak stands on Krotoszyńska Plate. Over the course of more than 300 years, Europe has seen periodic oak dieback spanning the area from Great Britain in the north to Romania in the south. It was first reported in Germany in 1739. The phenomenon of oak dieback has been known in Poland for more than 80 years, yet the most devastating losses occurred in the 1980s. A prolonged drought from 1982 to 1984, which followed the rainy 1981, caused mass tree dieback, first on Krotoszyńska Plate and then all over Poland. Particularly, many trees died in the following forest districts: Krotoszyn, Piaski and Karczma Borowa. Common oak was the most severely affected because of its shallow roots and less abundant root biomass. The symptoms of the disease presented both in the crowns and on the trunks. Smaller leaves, dieback of shoots and, as a consequence, thinning of the crowns and secondary growth on the trunks could be observed. Occasionally, sap secretions could be seen on the trunks in the form of moist brown stains. As part of the LIFE HESOFF project, assessment of the influence of phosphate fertilizers on forest health, experimental areas were established in the Regional State Forests Directorate in Poznań. Climate change exacerbates the phenomenon of deciduous tree stands dieback, particularly oak. To date, it has been scientifically proven that Phytophthora genus foreign invasive organisms are responsible for forest dieback. They cause severe damage to the root system, even up to 90%. The forest district of Karczma Borowa has a total area of approximately 13,000 hectares, of which nearly 10% is comprised of oak. They are stands aged between 100 and 140 years, and they have been causing us problems for many years. We have had a gradation of green oak moth, and we have, for the first time in Poland, chemically fought oak flea beetle. We have had massive deadwood for various reasons. Due to insects and fungi, so there were many problems with these stands. As far as I can remember, we have not done any planned treatments in the small oak complex nearby. All of the treatments have been sanitary. We have thus obtained large amounts of raw material. At times, it has caused disposal issues as our deadwood removal habits used to differ. There were years when we assumed that as long as there was one green leaf on an oak tree, we should not cut it down. There were also years when as soon as sap secretions appeared on the bark, the tree was to be cut down. Another thing, when the crown started dying, we would cut down the oaks and we would obtain full value material. Oak stands in the Piaski Forest District populate the area of approximately 4,800 hectares, which constitutes nearly 26% of the district's total area. For the most part, they are common oak stands. They grow on compact clay soil with very low annual rainfall. This is the main reason for permanent health problems of those stands, which have been particularly severe for the past 10 years. The problem began after the 2003 and 2005 droughts, as a result of which we were forced to remove approximately 15,000 to 18,000 cubic meters of deadwood every year. The main damaging factors are primary pests, folivores such as green oak moth, geometer moth or gypsy moth, which appear in gradation volumes every several years. Moreover, there is a secondary pest, oak splendor beetle, which appeared in particularly large numbers between 2005 and 2007, when more than 40,000 cubic meters of deadwood were removed. There are also root pests, i.e. the entire complex of pests damaging oak stands, which constitute the most valuable stands in Greater Poland and are located on the so-called Krotoszyńska Plate. Krotoszyń Forest District spans the area of more than 18,000 hectares. Oak stands comprise 38% of the entire district area, while in one of the sections they make up more than 80%. Most soils in the Krotoszyń Forest District, where oak stands grow, are rain clay soils created from glacial till. The winter of 1978-1979 was the winter of the century. It is believed to have been the beginning of the oak stand dieback process. After that period, in 1980, due to abundant rainfall, oak stands were flooded. However, 1981 saw massive drought which lasted until 1983, which may have had an impact on tree stand resilience. The drought also coincided with the gradation of folivores, which culminated in 1983. Deadwood culminated in 1984. The objective of the project is the assessment of phosphites as substances supporting tree resilience against invasive phytopathogens of the Phytophthora genus. We wish to implement and introduce as standard practice new assessments of forest conditions and planting efficiency using a stratospheric, long-flight crewless aircraft. The use of a crewless aircraft equipped with a multispectral camera as an innovative technology for monitoring the health of Polish forest complexes will enable an assessment of physiological parameters of trees, for instance chlorophyll fluorescence, as a tree health benchmark. Verifying the efficiency of phosphite preparations in forestry, administered by aerial spraying and trunk application, will allow to assess increasing the tree's resilience to phytophthorosis. After defoliation caused by insects, young leaves are particularly sensitive to infections with Erysipphe alphytoides. Probably, sporing of the fungus coincides with the development of new, young, sensitive leaves. Initially, only single white mycelium clusters are visible. Then they gradually spread onto the entire leaf surface. More often than not, the fungus strikes all leaves and tree crowns which, as a consequence, fall prematurely. Small roots forming mycorrhizal compounds and absorbing water with minerals from the soil die due to hypoxia during tree stand flooding. Yet these conditions are highly favorable for the development of pathogenic oomycetes. These fungus-like organisms, because they grow like fungi on artificial nutrients, are capable of creating motile spores, so-called zoospores. A torrential rain is enough for them to actively move through the water between soil particles in search of the slightest roots. After attaching themselves to their surface, they put down flagella, form a cyst, and begin the infection process. The affected dead rootlets are severed from the larger mother roots, and the pathogens remain in the soil, awaiting the next favorable weather conditions to attack again. They can survive drought, which is adverse to them, both as endospores, called chlamydospores, or as thick-walled conidia, called oospores. The latter are formed through sexual reproduction as a result of exchanging genetic material between the female and male forms, called oogonium and antheridium respectively. Oomycetes, as organisms whose biological cycle is closely connected with aquatic environments, develop quickly when tree stands are flooded, while beneficial mycorrhizal fungi perish in such conditions. These processes occur very dynamically in the mineral layer of the soil of up to 25 centimeters in depth. The damaged roots absorb less water, and the drying shoots provide fewer assimilates to the roots. In order to stop this adverse mechanism, the use of phosphites as substances strengthening plants' resilience has been suggested. We will now run a field test for the presence of phytophthora in oak roots. For this purpose, we will run a field test which we may use for testing plant tissue, for instance roots or trunk tissues. The point is for the tested tissue to be appropriately broken up and immersed in a buffer. After several minutes, we check with a plate test whether the result will be positive, 2 lines, or negative, 1 line. Such tests are currently not available for the Phytophthora genus, but also for other pathogens, for instance the related Pythium genus or the Rhizoctonia genus, as well as Botrytis crinaria, which causes grey mold. Phosphite fertilizers were administered to trees through the leaves during aerial spraying and through spraying of the trunks. The advantage of aerial spraying is its high efficiency and ultra-low volume of droplets, which reduces phytotoxicity. In the other case, the preparation permeates to the tree's conduits through live tissue between crevices in the bark. The procedure may be used selectively, which reduces administration costs. Only the trees with a good chance of recuperating are sprayed. We perform this treatment 3 times per year. It consists in spraying the appropriately concentrated preparation directly onto the tree trunks so that it permeates into bark crevices. The primary objective of using this preparation is strengthening the sprayed tree's natural resilience. The phosphites which were used, i.e. the form of phosphorus occurring as PO3-, are much better absorbable and mobile within the soil than the fully oxidized form, i.e. PO43-. On all the experimental surfaces, we observed, after administering the phosphites, a very significant reduction of exchangeable aluminium, which translated into increased plant health.
na wzrost zdrowotności roślin.
The phosphites were administered on this area in 2012 by spraying the trunks up to that height. Currently, the trunks which were sprayed differ in terms of color from those which were not. The main idea for using phosphites, the way they are to permeate, are bark crevices which lead to live bark.
W których znajduje się dostęp do żywej części kory.
The health of a tree may be determined by assessing its defoliation, i.e., the degree to which it sheds its leaves. For instance, the crown of the tree behind me shows 40% of leaves shed. However, it is a short-term phenomenon which may have been caused by foliophages. Therefore, what appears to be a better method is assessment using the vitality classification developed by the German scholar Roloff. Roloff distinguishes 4 vitality classes. Class 0, so-called exploration phase, when the shoots grow symmetrically and fill the entire crown space to form a sphere. Class 1, when the habitat conditions worsen, the lateral branches stop growing and the so-called twigs are formed. Consequently, a lance shape is formed.
Uzyskujemy formę lancy, tak jak moje palce. Kolejna faza,
Class 2, the so-called stagnation phase.
To jest właśnie przykład.
The crown behind us is an example of just that. During that phase, older shoots of several years are rejected by the tree as a stress reaction. This may be water stress or shorter day stress, a frequent occurrence in the fall. As a result, the so-called poodle's tails are created. At this point, the tree may survive many more years before dead branches occur, which is symptomatic of the third stage of crown damage, the so-called resignation phase, when the tree dies within several vegetation seasons.
Drzewo to zamiera w ciągu kilku sezonów wegetacyjnych.
Let us see now whether the trees with second stage damage during the stagnation phase also have damaged rootlets. The oak root which I have dug up has a highly reduced rootlet system. As far as I can assess, not many of them are left. Approximately 80 to 90% of rootlets have been damaged, with only traces of them left in the form of small points the size of a head of a pin. It is similar on the other root, yet in this case, 2 rootlets have characteristic mycorrhizae. Another root is practically devoid of rootlets. In this situation, the trees may have a serious problem with water absorption. Therefore, the most dangerous situation is the transition from a vegetation year with abundant rainfall to that of drought. A working hypothesis of the HESOFF project assumes that if we succeed at protecting the root systems, particularly the rootlets, eventually, after several years, the shoots in the crowns will also rebuild themselves. How to do it? We wish to use phosphite preparations. They are fertilizers containing various forms of phosphites, PO3 ions. Not only do phosphites affect pathogen Simelium directly, but they also induce resilience reactions. In the presence of phosphorus, the cells know that they are being attacked by pathogens. It is due to the fact that we make it impossible for the pathogens to mask the infection. Because of that, the cells may prepare for the pathogen attack. They produce many biologically active substances, the so-called phytoalexins, and, as a figure of speech, also seal their cells by producing additional layers of parenchyma cells. Most importantly of all, however, a signal is transmitted to other cells so that they can prepare in advance for a pathogen attack. What may also be a symptom of the weakening of a tree is the presence of Kermes quercus, which suck out the sap from the bark crevices. They are visible in the form of brown balls. Each specimen injects tree cells with enzymes which cause the cell to grow and make it easier for it to suck out the sap. If many of them are concentrated in one area, its tissue becomes deformed and the tree is further weakened. Due to cooperation with the Institute of Aviation, new possibilities have emerged of assessing the trees not only from the ground, but also from the bird's eye view by using a specially fitted drone and a multispectral camera. The obtained photographs may also be compared with satellite images. Research using spectrometers and teledetection measurements with the use of Quercus 6 multispectral camera is supposed to help develop a method of early detection of disease symptoms visible as fluctuations of the course of spectral signatures within visible radiation and infrared ranges. Learning of the early stages of disease development creates an opportunity of precise tree protection and economic loss reduction. The orthophoto map visible on display shows tree stands of Krotoszyn. There are approximately 60 trees which we research in that area. 30 of them are reference trees and 30 are fertilized with phosphites and monitored using teledetection methods. During fieldwork, we collect samples which are used for assessing tree condition. Images and measurements are taken periodically, every year. We try to collect aerial images at least once a month. These images are used for developing a unified methodology. We wish for the HESOFF project to result in a benchmark to be applied by foresters all over Europe. In order to develop a teledetection benchmark, which will help determine the condition of oaks, we will have to avail ourselves both of laboratory and specifically teledetection methods. We had to verify the correlation between particular parameters obtained by 3 methods and to determine the influence of those parameters on tree conditions. We have built a special station for obtaining spectral signatures. The station is unique in that it enables us to simulate the field conditions during aerial maneuvers. At the station, we place the studied object in a special space. This space is illuminated with special light bulbs which emit electromagnetic radiation with a spectrum similar to that of the sun. Thus illuminated seedling imitates the conditions during aerial maneuvers. We collect the spectral signatures and then cross-reference them with the data obtained from aerial images. A comparison of all this data will allow us to assess the effects of using phosphites on control and treatment areas, particularly within groups of healthy and sick trees. The first results obtained in the course of the project were presented in July 2015 during an international conference in which foresters, biologists, phytopathologists and entomologists participated. The process of oak dieback has been visible in Poland for several decades, particularly for the past 20 years. Thus, its causes have been long diagnosed, both in terms of abiotic and biotic factors. Is there a more pressing issue than forest protection? If we are able to apply our knowledge and work to attain this grand objective, we will do what is expected of us. We would like to increase the health of oak stands by improving the root system structure and rebuilding crowns. We also wish to develop a new, environmentally friendly method of monitoring the health of trees in Polish forests.
I will talk today about Phytophthora species because just that there is a link between the presence of these Phytophthora species, the damage that they can cause to the roots, and then the effect that we see by eyes, because an infection with Phytophthora species, it just mimics a drought stress.
This is an open way, and we can work in this way in order to produce a map risk and a prediction formula that fit different disease systems. We want to use next generation sequencing to detect species, especially because we want practical solution. We want to use practically the outcomes. And that means that we have to know if the pathogen is alive or is dead. We are able to detect new or unexpected species.
Root infections with Phytophthora pathogens lead to many levels of changes in a plant organism: morphological, physiological, and genetic. Genetic research constitutes a crucial element of the project because it provides invaluable information about the presence of pathogenic DNA in the researched oak's rhizosphere. The infected rootlets are severed from the mother roots, which is why it is very difficult to isolate the pathogens from the root systems. However, species of the Phytophthora genus, particularly Phytophthora quercina, maintain residue presence within plant remains, where they wait for favorable conditions to attack again. This presence may be detected using molecular biology methods. The extracted DNA is multiplied in the course of a polymerase chain reaction, PCR, and then the characteristic DNA sequences, so-called ITS, are analyzed in order to identify the pathogen species. Another aspect of the HESOFF project is the search for efficient biological protection of oak rootlets with the use of antagonistic bacteria on Phytophthora genus pathogens. Rhizospheric bacteria are isolated from the rhizosphere of oaks on Krotoshin plate. In laboratory conditions, we verify their antagonistic properties. The left-hand dish is the control dish, where Phytophthora grows normally. Yet the right-hand dish has a culture consisting of rhizospheric bacteria and the Phytophthora pathogen, which is inhibited by the bacteria. Selected strains of bacteria which display antagonistic characteristics, i.e. they inhibit the growth of Phytophthora, will then be used to produce biopreparations. All 180 research trees were sampled for leaves from well-lit top sections of the crowns and for the same number of collective samples of soil around tree trunks from the depth of approximately 25 centimeters. Analysis in terms of nitrogen, phosphorus, potassium, calcium and magnesium content were performed once a year, thus building a unique database. Not only did it enable us to learn about the influence of the treatment, but also about the natural processes taking place in oak stands, e.g. habitat acidification. Unfortunately, in order to collect the shoots, we have to climb to the treetops to the so-called luminous crown section and to assess the leaf physiology in real time using the Handy Pi camera. This will enable us to compare the trees which were and were not treated with phosphites, whether their physiological condition remains the same or begins to slightly improve. We can observe that these shoots have already been damaged to a great extent by defoliating insects. In this case, the entire blade. As much as 40% of the leaves have been damaged by insects. This is interesting because sessile oak is less eagerly eaten by defoliating insects than common oak. In this case, we can see less damage due to insects, but more damage caused by HESOFF alphytoides, visible in the form of white mycelium on the leaves. If strongly present, it causes second defoliation, first by insects, primary pests, and then because of HESOFF alphytoides. We are now in Piaski Forest District, where we are collecting so-called soil monoliths. They are nuggets of soil sized 20 by 20 centimeters, which serve several purposes. First of all, from the collected soil, we are able to isolate the Phytophthora genus pathogens which infect rootlets. Second of all, the monoliths contain a certain number of roots, which are then scanned and analyzed in terms of root length and many other parameters, owing to which we are able to determine Phytophthora genus pathogen activity. The samples collected in the forest are at this point further processed. Above all, we separate the oak roots which we are interested in from those of other plants, grass or hornbeam. We also separate honey fungus rhizomorphs. Then the soil is mixed and we collect samples for genetic analysis. Owing to these analyses, we are able to precisely determine which species populate the soil. To date, approximately 14 species of the Phytophthora genus have been detected. Studying soil samples and leaf chemistry, we will be able to tell whether the roots function properly. If the roots contain all the basic elements which are missing from the trees, it means that the tissue is with the elements absorption by the roots, e.g. damaged by Phytophthora genus pathogens. Thus prepared roots may then be studied in terms of a variety of parameters: length, surface, number of tips, using a water scanner. The water scanner differs from the regular one in that it has a water cartridge in which we are able to spread the roots appropriately and then scan them. It also has additional lighting from above, which eliminates shading. Due to that, the image enables us to select the rootlets by size. What we are most interested in are the roots sized from 0 to 2 millimeters and from 2 to 5 millimeters. The image on the computer screen enables us to differentiate these root sizes and segregate them accordingly. Sever in order for them to be weighed and for their dry mass to be determined. We need it to compare the health of treated and controlled trees. What we have in mind is preserving as many of the small roots as possible and protecting them using phosphite preparations. Rootlet analysis is essential to assessing the treatment efficiency. It is already visible with the naked eye that the oaks treated with phosphites have more small roots than the control oaks. Additionally, from the collected soil samples, we prepare a small batch which is sent to a chemical and agricultural center. The center determines for us the physical and chemical properties of particular soil samples, while our colleagues at the laboratory handle checking the number and diversity of soil bacteria. The first component marked was pH, which was very low, from 3.1 to 3.6. The presence of exchangeable aluminium was was also associated with low pH. Exchangeable aluminium, as we know, is responsible for damaging plant root systems, particularly in the absorbent hair section. What was typical of all the research facilities was very low saturation of the sorption complex with alkali, which oscillated around 10 to 13%. Oak leaf spectral curve measurements, taken with a spectrometer while still in the field, allow for a preliminary assessment of the tree's physiological condition. They are later supplemented with laboratory research conducted by a specialist laboratory at the Horticulture Institute in Skierniewice. Apart from chlorophyll and carotenoid content, they also include brown pigment content, other than chlorophyll, per leaf surface, which are responsible for plant aging. Also analyzed is water and dry matter content for leaves collected from particular control and treated trees. This data will be used for developing a proprietary pro-sale model. Summarizing the project results, we are pleased to have been able to protect oak rootlets which absorb water. The treated oaks had much better rootlet morphology parameters. Out of 8 studied factors, 7 were significantly improved in Krotoshin Forest District. Slightly more modest results were obtained in Karczma Borowa and Piaski Forest districts, but even there the surface and length of rootlets differed so that they were statistically significant. This gives us hope that the improvement of root systems will also influence rebuilding of crowns in the foreseeable future. Thus, the anticipated health improvement will be visible long after the project has been concluded. It is estimated that the effect of phosphites ought to last approximately 6 to 8 years.